Log on, tune in, find out. Another good idea from Cambridge.
Second speaker this afternoon is Shepherd-Barron, who's talking on stable shock.
Thank you very much. Thank you for the invitation to talk in this program. The program has a avowedly non-abelian focus, but what I want to talk about today is abelian. So we start with the following classical situation. I've got the moduli space of curves, and I map it to the moduli space of principally polarized abelian varieties. The curve maps to its Jacobian, which comes with the principal polarization. And let's say that the closure of the image, so this is one-to-one on points, JG bar is the closure of the image. And of course, this is strictly smaller than the moduli space of abelian varieties as soon as the genus G is at least 4. So the Schottky problem, or I'm a little confused, I haven't bothered to investigate the history too much. It might be the Schottky problem, it might go back to Riemann, but it's usually known as the Schottky problem. So the statement is to characterize, find ways, characterize the image. So, for example, from one point of view, there's a complete geometric solution by Khrushchev. If you've got a principal, an irreducible, if x lambda is a point in AG and is irreducible, then it is a Jacobian if and only if the Kummer variety has a trisecant. All right. But in fact, the original approach to the problem due to Schottky's approach was to try to find equations defining and of course, if you want to describe a geometrical object in terms of equations.
Nick, can you just remind us what the Kummer variety is?
Okay.
There's a subvariety.
Yeah, so if I start out with x and lambda, it has on it a linear line bundle which defines twice the principal polarization. So I can map this via some linear system which has no base points to a projective space of dimension 2g minus 1. And then the Kummer variety is the image. And in fact, if x is irreducible, then this is an embedding reducible. And let's just go back and say something which I don't think trouble anybody in the room. I'm working over the complex numbers. So when we talk about the Kummer variety having a trisecant line, I mean, I look at the Kummer variety sitting in projective space and ask that in that projective embedding, it have a trisecant line.
Is this obvious in either direction?
No. Oh no, it's a major theorem.
In both directions?
Yes, well, it's in one direction it's quite, I mean, I suppose it's in one direction, proving that the Kummer variety of a Jacobian has a trisecant follows from phase trisecant identity which, well, Fay himself has a two-line proof in the Bowden proceedings, depending upon which is a very cunning consequence of the residue theorem. But no, I mean, so one way is quite short, the other way is a really major piece of work, and I shall say no more about it, because today I want to talk about equations. Alrighty, so this is today. Okay. Well, ideally, if you're going to try to solve a geometrical problem by finding equations, you would like the equations should be well, what should they be? They should be explicit. They should be complete. And they should be comprehensible. Okay, well, this is the basic problem in algebraic geometry, but this is almost never the case. But this is, if you're trying to combine algebra and geometry, this is what you would like. But let me immediately point out this is kind of difficult. If I look at the locus J1 G minus 1 sitting inside the closure of the locus of Jacobians, so by this I mean, let me just say colloquially, this is the locus of elliptic tails. Or if you like, if I let a curve of genus G degenerate, this G, if I let it degenerate into a curve of genus G minus 1 and another curve of genus 1, then the Jacobian here will specialize to the product of two Jacobians. So this locus here is meant to represent that picture. So this is codimension 2. Okay, so here I have a curve, let's call it gamma, of genus G minus 1 and E of genus 1. Then J bar is singular along J1 G minus 1, and for generic gamma, the singularity is the cone over gamma, canonical model of gamma. Okay. So in other words, if you had a completely satisfactory solution to the Schottky problem in genus G, then you would have a completely satisfactory understanding of the equations of a canonical curve of genus G minus 1. And it's well known that we don't have such an understanding. So I will then say, well, I've set myself a problem which is too difficult, and I will simply look for anything at all that I can grasp. So I will settle for something which is both explicit and comprehensible and give up on completeness. Okay. So this is what Schottky actually did. So Schottky.
What do you mean by complete?
Well, let me show you let me show you something, and then you'll be able to decide for yourself how comprehensible it is.
No, complete.
Sorry,
What do
complete.
you mean by complete?
Sorry, can you repeat the question?
What do you mean by complete?
Well, I mean a list of equations that actually defines the ideal of the subvariety. Okay, so well, I mean, I'll remind you of what Van Gemen did. So briefly, Schottky showed how to write down certain equations, and Van Gemen then showed that the equations that Schottky found have the Jacobian locus as an irreducible component. So in that sense, the equations that Schottky finds are not complete. Okay, so what did Schottky do? He did this. Okay, So given a point in the moduli space, fix a level 2 force structure. It doesn't really matter what this means, because it means it's a small amount of extra information. So this level structure, this gives a projective space, the same one as above, with a fixed coordinate system, a canonical coordinate system. So the key slogan to mutter here is, this is the representation theory of theta groups. Okay. So exactly as above, we get let's call this Ix, that's not an embedding, and then you get a morphism for the moduli space with this extra finite structure to this projective space by X maps to the image of its origin. So of course, remember when you're constructing moduli spaces, you're trying to replace an algebraic variety by a single point. Now, of course, these moduli spaces are not compact, but moduli of abelian varieties have Schottky compactifications. Okay, well, I suppose I'm inverting history here. Schottky would have had an easier life if he'd known about the Schottky compactification. But I think, oops, sorry. Yes. And this works at finite level as well. Okay, and the boundary is a union of copies of the same moduli space, but at genus 1 less. Oh, and also, let me go back to here, this image satisfies explicit equations essentially coming from the representation theory. So the point is that the linear algebra gives you a model of the moduli space, and you can write down explicit polynomial equations. At least you can write down a subset you can write down a set of equations which is contained in the ideal that defines the moduli space. Okay. All right. So we have so this map from the moduli space to projective space extends to the Schottky compactification. I get by looking at a boundary component that sits inside there, that maps to a smaller projective space, which sits in there. This is a linear embedding. So it's a linear subspace of about half the dimension. And then we have this abelian variety sitting in the same Moduli space. And its Kummer variety sits in the same Moduli space. So if I look at the intersection of X with the smaller subspace, this is a finite set. It sits inside the 4 torsion of X, in fact. Okay. All right. And then what Schottky showed was that if X is a Jacobian, then in fact, then X meets this thing here. Right, so every X meets this linear space. Jacobians meet this smaller Moduli space. And it meets it, in fact, in the Moduli point of a prim variety. So then the equations, the known equations, the known explicit equations that constrain AG minus 1, level 2, 4, constrain the point of X. The Moduli point of X, in a way that can be made explicit. All right, so I keep harping on the word explicit without actually being explicit, but I will be explicit in a while. Okay. So what Van Hemeren did, he showed that the Jacobian locus at level 2, 4 is an irreducible component. Of the locus defined by these equations. So I should say one thing, that the equations you get here that I'm referring to depend upon simply come from the fact that this X meets this sub-moduli space. The fact that it meets it in the point of a prim variety is not as relevant as the fact that it's simply meeting it, that you get some abelian variety out of it. So in other words, as far as I can tell, we do not know how to exploit the fact that here you get a prim variety. Obviously, in large genus, the locus of prim varieties satisfies further equations. This construction here merely uses the equations that are defined on the whole moduli space, not the further equations you get from the prim condition. Okay. Okay, so this is what Van Gemen did. What Schottky actually did was to look at genus 4. Schottky was genus equal to 4. Okay, so so A3, this is the dimension here is 6. So the Schottky compactification lives inside P7, so it's a hypersurface. Defined by one explicit equation. So you get, so he got one explicit equation for the Jacobian locus in genus 4, sitting inside A4. And this indeed is a codimension 1. Okay, this is 9-dimensional. This is 10-dimensional. All right. So, again, this word explicit. So I actually want to write down some explicit functions on the moduli space. So these are provided by theta series. Okay. All right, I have to confess, I have a hard time distinguishing between bilinear forms and quadratic forms. You'll have to put up with that. Suppose I have B, z to the r cross z to the r, z, and bilinear, even, and unimodular. Even, unimodular, oh, and positive definite. So this is a bilinear form. If I want to think of B as a quadratic form, I'll write it as Q in a way which is rather objectionable. Okay. So these such
Nick?
yeah.
But is it symmetric?
Yes. Okay. All right. Yes. Without the symmetry condition, this really would be a horrible thing to write. But okay, I'm sorry about that. Okay. So I shall think of this as a lattice. So B, or I'll call it Q. Okay. So remember that there are some very lovely theorems. These conditions imply, for example, that R must be congruent to 0 modulo 8. And they do exist. And I'll remind you of some explicit ones. So I get, from this quadratic form, I get a theta series in genus G. So if Tor is a period matrix, that means Tor is a point in Siegel space, which consists of, so this means that Tor is symmetric, and the imaginary part of Tor is positive definite. This is the period domain for principally polarized abelian varieties. So I get, from a quadratic form, I get a theta series, which is the sum, I haven't left myself, sum over x1 through xg in z to the r, and then the thing I'm going to sum is x pi I, sum over all pq from 1 to g, of b of xp, xq, Tor pq. So the point about these theta series is that each theta series it's actually a scalar valued modular form for the full modular group. But I can think of it then as a section of a line bundle, which is on the Schottky compactification of M tensor R over 2. So M equals the line bundle of weight 1 modular forms. Okay, so what I'm saying is that if I've got a quadratic form like this of rank R, my theta series is a modular form of weight R over 2. Okay. So if R is equal to 16, it showed that if R is equal to 16, there exists exactly two quadratic forms Q, namely E8 plus E8, and something else which is a little bit bigger than the root lattice D16. So D16 plus indicates that it's a little bit bigger than D16. Okay, and then Igusa showed that Schottky's explicit relation, Schottky's relation in genus 4 is theta E8 squared minus theta D16 plus equals 0. Okay. So finally, I have something which is explicit. So notice in particular that we've got down, so previously, when I was discussing Schottky's construction, I was at some finite level structure. So Schottky actually found relation at this higher level, and then Igusa showed that if you push it all the way down to level 1, this is what you get. Okay, so I want to stick with theta series. All right. So modular forms behave very well when you restrict to the boundary. Okay. So via AG minus 1 Schottky, embedding into AG Schottky as the boundary. And this is at level 1, this is the entire boundary. You get, you have a homomorphism, Siegel's phi operator, sorry. And a theta series for Q at genus G maps to the theta series for the same quadratic form, but in genus 1 less. Okay. So Freytag proved a wonderful theorem about how these spaces of forms stabilize. So phi, this is a slight abuse of notation because it depends upon G and K, but this restriction map is an isomorphism if the genus is large compared to the weight. And then we can take a look at the following ring. Direct sum over all K. And then observe, we can write it, this is the same thing as the inverse limit over all G of the direct sum over all k with this inverse limit is in the category of graded rings. Alrighty. And he showed also that this ring is nothing but the polynomial ring in the set of all theta series. Oh, okay, I've taken a set of representatives of the quadratic forms. This is a polynomial ring. So, what you've got, so I can think of this actually, right, let me just leave it like that. But do not get too excited by this, but AG Schottky, this does not mean that the Schottky compactification of AG, so this is not stable at a projective space. For one thing, it's a general type as soon as G is at least 7. Okey-dokey. Alrighty, so what Freytag's result tells us is that this ring of modular forms simplifies under stabilization. So this R is the ring of stable modular forms. But the Schottky compactification stabilizes as well. So if I look at the, oh, sorry, wrong place.
Here when you write AG, you mean AG24?
No. Ever since the whole point is that these theta series are modular forms all the way down at level 1. Okay? So this is the union, or the direct limit if you like, G. Okay. Well, okay, so this is infinite dimensional, but it does have a multiplication. Which extending the obvious map okay, and its identity is the point at infinity Alrighty, so this ring R, which I'm looking at, is the ring associated to some line bundle on this. So I can think of R So this is a graded ring. This has a co-multiplication. So covering the multiplication and you can write this down in terms of theta series very simply. The co-multiplication is theta q maps to theta q tensor theta q. So this is a graded ring the co-multiplication structure is somehow graded, but this is not a graded Hopf algebra in the usual meaning of that phrase. So be a little bit careful. Okay? So why does this the fact that the co-multiplication looks like this simply says that theta q, if I take two matrices sigma and tau and put them together into a block, then this is theta q of sigma times theta q of tau, which follows immediately from the definition of the theta series. Okay, and it has a co-identity theta q maps to theta q evaluated at E, which is 1. Okay. So in other words, what's going on here so r plus or minus, well, I could take C so this is the coordinate ring of an algebraic torus whose dimension is large, it's true. And R is the coordinate ring of a torus embedding. Okay. Alrighty, so now we go introduce Jacobians. So if I define JGS equals the closure of JG in AGS, okay, I can then take the union of all of them and this too is closed under multiplication. And of course it contains the identity. Okay. So we have a ring homomorphism R. I could look at simply a restriction map, and I is its kernel. So I can simply define this to be the ideal of stable Schottky relations. Okay. And I can prove a theorem about it. Well, I'll call it a theorem. So I is generated by differences theta p minus theta q. So the point, I've erased what I wrote down earlier. But remember that Igusa showed that in genus 4, the single modular form that cuts out the locus of Jacobians is exactly a difference of this kind. So compare this to theta E8 squared minus theta D16 plus, which is in genus 4.
Do you say which differences?
Say again?
Are you saying like which differences?
I don't know. Oh, no. That's, I'm sorry, yes. I mean, Damn, you asked the right question, but slightly too soon. Okay, so since it's so easy, I'll prove this. Okay, well, since the multiplication on A preserves the multiplication on J, A infinity preserves J infinity, so I times R plus or minus is the ideal of a subgroup of T. But in an algebraic torus, every subgroup, an algebraic torus has coordinates, every subgroup of a torus is defined by equations like this. Every subgroup of a torus is defined by equations chi1 minus chi2 equals 0 for characters chi1 and chi2 of T. Okay, so if I clear denominators, then I prove my theorem. Right, so now we come to Bert's question, which differences? And I don't know. Now, the point, so, let me, when I got to this point, I thought I was doing something really interesting. But the truth, I've a horrible feeling that actually it's not. So, is I equal to 0? I mean, I can't prove that it isn't, I can't prove that it is. But I can prove for you that what I can prove is sort of has a slightly negative flavor.
So your Eugene's 4 relation doesn't survive?
It does not survive. This is already proved this was proved quite recently by Gruszewski and Savattimani. I'm going to talk about their result, in fact. Okay. So I have to make a rather boring definition simply to state the result that I can prove. So, definition, so Q is my quadratic form, even, unimodular, positive definite. Q is lambda balanced lambda is some scalar if essentially Q of x is lambda times the sum of all delta R of Q x dot delta squared, R of Q, the roots in Q. Strictly speaking, the roots in the lattice on which Q is defined, I'm sorry. So for example, E8 squared D16 plus are 1/60th balanced. Well, okay, it's easy to prove. And now I can prove the following proposition, which generalizes well, I'll tell you, let me write it down, say something about the proof, I suppose. Proposition, if P and Q are both lambda balanced for the same lambda and of equal rank, then the difference is not in the ideal. Okay. Or let me, all right, so in a desperate attempt to retrieve the situation, let me state this in a positive way, i.e., there exists a Jacobian period matrix that distinguishes P and Q, P from Q, I should say, sorry. But you don't know that it's genus. You do not know the genus. Okay. So I'll say something about the proof. So Gruszewski and Salvati-Mani proved that the Agusa form, or the Schottky form, does not vanish in fact, it cuts out the locus of trigonal curves in genus 5. Okay. Star is that hypothesis there. Okay. What in fact, their argument does the following. Is this. So if you assume star, okay, and assume that theta p minus theta q vanishes along JG. Okay. Then it is singular, this difference, is singular in genus 1 less. Now, singular at the stack level. Okay. So, of course, I haven't, who would, emphasize the difference between the coarse moduli space and the moduli stack. But I should point out that everything we're doing here depends heavily on this multiplicative structure. To have this multiplicative structure, I must be at the level of coarse moduli spaces. If I try to define a multiplication on stacks, I run into horrible problems of homotopy. I don't even have a two-sided identity. And if I don't have an identity, on an infinite dimensional monoid, if I don't have an identity, I really can't do anything at all. Okay? So everything is really happening at the level of coarse moduli spaces, except that a little bit is happening at the level of stacks. Okay, so for us, I think I don't have, well, I probably won't have time to say anything much about Gruszewski, but their argument is very geometrical, and it relies upon the fact that in a Jacobian, if I've got a curve C, I've got a difference surface sitting inside the Jacobian, the degree 0 Jacobian. And their argument depends heavily upon the fact that every second order theta function vanishing along this different surface, C minus C, has a fourth order singularity at the origin. Okay. So this is a result due to Van Gemen and Van der Geer. And it's a very surprising result, because if you've got a curve of high genus, this is a singular surface. The singularity again looks like the cone over the canonical curve. So the singularity is defined by lots of quadratic equations. But what this is saying is that the theta functions, the second order theta functions, in fact have fourth order singularities there. Okay? So they use this result and then plug in the heat equation. Heat equation, which tells you that some second order, so if you've got second order theta functions with fourth order singularities in the z direction, then you get singularities in the tau direction. That's what the heat equation tells you. Okay? But for the heat equation to work, you need this lambda balance condition. Okay. Alrighty. So this is the geometry which underlies the Gruszewski and Savati-Money result. So let me take their result and plug it into the stable situation. Well, what have we got? No eraser, apparently. Okay, so for us, so let me call this F union of FG's, the zero locus of this difference sits inside A infinity here, and is singular, so E is, the identity sits in E, and F is singular along Jacobian locus. Okay. But on the other hand, remember that I've got, well, what do I want to say? That F is also closed as a submonoid. Okay, of A(S) infinity. Okay. So, by the result of Cartier and Shafarevich, Cartier in finite dimensions, Shafarevich in infinite dimensions, F is smooth in a neighborhood of E. Contradiction. Okay, so I should say that this, right, the question at the top is still open. I have this ideal of stable Schottky relations. I know that it's generated by differences of theta series, but I don't know that it is, unfortunately, I do not know that it is actually interesting. I slightly suspect that the answer is, if I can prove anything at all about it, that I'm going to be able to prove that unfortunately it's not interesting. So let me try to retrieve things slightly by saying, well, in fact, I could play the same game but look at the hyperelliptic locus, but compare the hyperelliptic locus let's set the genus go to infinity. So the same, we have the same structure theorem. For the ideal of stable relations, ideal I hype of stable relations. Okay. And Poor showed that the Schottky relation, what is it, theta d, squared minus theta d16 plus is in this well, hyperelliptic curves are well known to be much, much easier than generic curves, of course, so this doesn't really count. But I should say that this argument of Khrushchevsky and Sarvati-Mani, this modification of their argument, depends on this lambda balanced hypothesis. And I hope that this is simply a defect of the argument. The argument depends upon looking at rank 1 degenerations. So if you look at rank 1 degenerations, then from an even quadratic form Q, you're naturally going to be picking out the set of roots in that lattice. But if you it's possible, it seems to me, that if you look at higher rank degenerations, then you can get beyond this restriction of only being able to see the roots in the lattice, and you might be able to go further. I'll stop there. Thank you for attention.
Any questions?
I have a very elementary question. Suppose you have two quadratic forms,
Yep.
bilinear forms, which are orthogonal.
What do you mean right? You mean different orthogonal sublattices?
Orthogonals.
Yeah.
Then the corresponding thetas will be the product.
Yeah.
Will be the product. Right?
That's right.
So suppose two quadratic forms
Mm-hmm.
are stably equivalent in the sense that you add the same. That is p plus q1 is equal to q plus q. P plus q dash is equal to q plus q dash.
Right.
Then presumably you will get theta p. Then they are equivalent. Suppose
So you've got
p plus q1.
well then. So wait a minute. You've got Q1 and Q2. So direct sum P
Yeah,
is isomorphic to Q2.
plus p.
Direct sum P. Okay.
Then the theta will be product of theta q1 theta
That's
p.
right. So theta Q1 will be equal to theta Q2 therefore.
Theta p.
But wait, this is not. Wait a minute. We're talking about even unimodular things, right?
Yeah, assuming both of them are there.
Right. So I think what we're saying here in that case, because the theta series are, so then theta Q1 is equal to theta Q2, because I can cancel the theta p's, right?
That's right.
Okay.
That's right.
But then I can read off. Can't I read off from that?
So how do you say that these two are distinct? You say theta p minus theta q is not the ideal. So suppose q1 and q2 are stably equivalent in this sense.
Well, all I can ever say, and the point is, I'm interested in the theta series rather than the quadratic forms. Sorry, maybe I misunderstood your.
No, I think I misunderstood you perhaps. So, you wrote a proposition here saying theta p minus theta q is never in I if
Where? Sorry.
that's erased. It's below that, right?
Down here?
No, after you said you defined balanced, lambda balanced, which I don't understand very well.
Okay, sorry, that's just, the only point of that definition is only in those circumstances that I can prove anything. So it's a technical constraint it's a boring technical constraint on the quadratic forms imposed by my inadequacy.
So is it true, just a side question, is it not all Q are lambda balanced?
No, they're not.
But lambda is a function of Q.
Lambda is a function of Q, even if it is lambda balanced, yeah.
Nui thing.
It's a Coxeter number thing, actually.
Oh, even simpler.
Yeah. Because if I take two quadratic forms, if they're both balanced but with different lambdas, then their direct sum will not be balanced.
No, going back, if
Yeah.
so theta q only depends upon this equivalence.
But if as soon as the theta series are equal, then I think I can deduce, because the theta series counts the number of, just look at that.
Yeah.
That theta series counts the number of ways of embedding all quadratic forms into Q1. Okay? So if theta Q1 is equal to theta Q2, for all G, right, if the two theta series is equivalent for all G, then Q1 must be isomorphic to Q2. Because the theta series counts, I mean, as I say, just for a fixed quadratic form, this theta series for all G will detect all embeddings of all quadratic forms into Q1.
Any more questions? Okay, can we thank Nick again?